Okay, good afternoon, everybody. So we will start by a keynote talk given by Anthony Lin. So he is an expert in automata and logic from MPI and then University of Kaiserslautern. And then today he will talk about like transformers, the one from Gen AI, and then to understand it from the angle of automata and logic. Thanks, Anthony.
So thank you again for the introduction, and thank you again, Yifang, Thomas, and Ondra, for inviting me to give a talk. So this is, by the way, a topic that I don't usually talk about. So I've started working on the topic pretty much the last 3 years ago. I guess so. When I was invited to give a talk, I thought like, okay, I should give a talk about something that is a little bit different that you don't normally listen to at VMCAI. So this is why I came up with this topic. So, but hopefully I can convince you that logic and automata and verification have its place when you want to understand transformers and when you want to, analyze and get better understanding of transformers. So maybe just a very quick question. So how many of you know a bit about, okay, so I guess everybody has used LLMs before, obviously, right? This is not to us, I guess. But how many of you know a bit more about the architecture of the LLMs, let's say transformers? Can you raise your hands? Okay, yeah. All right, okay. So I will go through it a little bit more slowly, because the notation is also a little bit different anyway. So, but anyway, so without needless to say, so transformers is so transformers are a model that was proposed around 2017, around this time. The purpose was to overcome the limitation of RNN, and this was. Took a picture or screenshot of this like around a few months ago. I'm sure it's now become like, 200 something thousand, so the number of citations here. But this is the basic model behind today's popular LLMs, some of you might have tried some of this one, so maybe GPT or Gemini or others. Okay, but transformers, if you think about the model itself, so transformers as a model, these are an inherently sequential model. That is, so what does it mean by sequential model? So what it means is that the input is a text, it's a sequence, it's a text, sequence of tokens. Typically, you don't really have a bound on the size of on the length of the sequence. So unlike classic feed-forward neural networks, so you get a sequence or a text like this, and when you run transformer on a text, the output is also a text, Could be, for example, something like this, Okay. So what I mean by transformers in general, I don't really mean a specific large language model, foundational model. I actually just mean like the architecture of transformers itself. So it could be a much smaller one, Okay, so of course we know that transformers can do a lot of amazing things, but interestingly, transformers are also known to be bad at certain things. So, so this is, for example, a task that is known to be quite difficult for transformers, that is doing counting and doing arithmetic. So this is an example that no longer works, I actually tried it about a few months ago. It worked, and then now it doesn't work anymore. But anyway, let me just show you. So for example, it's pretty small. I'm going to try to read it for you. So for example, you can ask GPT to count the number of A's and B's. This is like a really trivial example, but just to give you a simple example, it's not so obvious. So I'm going to give a string A's and B's, of A's and B's. And then you ask GPT to tell whether or not there's an even number of A's or even number of B's. So this is a very basic, simple kind of counting, So in particular, you just need to know, like, you just need like one bit to know, right? Like to remember whether or not this is the parity of the number of A's. Okay, so after some after some conversation, you can, for example, input some string like this, and then what it says here is that, okay, so for example, this is the output is like this, let's say 19, it has an odd number of A's. Yeah, but unfortunately, if you run this, yeah, like using Python, for example, actually the number of A's is actually not really 19, it's actually 22. Okay, so this is one such example here, yeah, so that epitomizes the problem with counting. And this anomaly was actually found already some time ago, yeah, in particular by these groups of authors. So in particular, there was they consistently showed that there's a problem when you want to train a transformer to recognize the regular language parity. That is basically, when I say recognize, I'm talking about to classify the strings that belong to this language. So it's a very simple classification task, yeah. Okay. So of course, when you see this kind of phenomenon in an experiment, what you want to do is you want to try to understand, like, is this actually even expressible by a transformer? Is this, if yes, is it really trainable? Right? And this is, in fact, one of the main questions that has driven the field of connecting formal languages and neural networks. Yeah, and in particular, there's quite a lot of people that have already started working on it. So it has a highly active Discord channel with 500 plus members. Yeah, and rapidly growing number of publications as well at top ML venues. So let me just show you super quickly here. It's a bit small, but actually the main results in the field were from, like 6 years ago, 5-6 years ago. In particular, this result that actually shows that parity is quite difficult for transformers. But on the other hand, you see something that looks a little bit contradictory. So parity is difficult, but then how come it's transformers are Turing complete, right? So you see that when you get into the field, you always get this kind of feeling that how come everything looks contradictory? So we will talk more about that, yeah, during the course of the talk. And one thing that I can say is that there's quite a lot of different models that people look at. Yeah. So in particular, so this one here, like a lot of people used to, and actually still think about transformers when it's kind of like doing shallow thinking. So this basically when you this is like as an analogy, maybe if you run GPT, you want to get an answer quickly, right? You don't want to wait for too long. So if you're happy to wait for a long time, yeah, then maybe you can solve more. Yeah. So this is basically the this thing about chain of thoughts. Okay. In particular, so these are the results that have been around, and you can also ask, what can transformers do in general? Like if we already if you want to use regular languages as a guide, as we are verification people, can we classify any regular language? Can we solve any computable functions? And also from the point of view of programming languages, yeah, can we provide a clean declarative language that characterizes the expressivity of transformers? Yeah, and so these are like really fundamental questions. If you want to do any analysis or verification, you first need to be able to have some kind of semantics, right? So so once you have this, which is actually not even solved here, not fully, you also want to ask, can we automatically verify transformers? Like, is this even decidable? Can we exploit verification techniques like IC3 and stuff like that? And if you want to like relate it to something that also appear in practice, yeah, there are so many kinds of LLM attacks out there. Yeah, can we also use this to verify LLM attacks? Yeah, against LLM attacks. I mean, this is a bit far away, yeah, but I just want to show you that this is probably what we want to reach, but this is not really. We are nowhere close to that. Okay. Just checking the time. Yeah, so this is the outline of the talk. So I'm gonna mainly focus on the kind of formal models of transformers. Yeah, I'm gonna take you guys through the examples. Yeah, and I will mention some what can be done for verification, throughout the talk. And also, I will make a remark. So most of the stuff that I'll talk about is they basically concern models with no chain of thoughts. Yeah, basically the ones where that are mostly used, yeah, in practice. But if you want to use chain of thoughts, yeah, this can be done. So we will talk as well about that. But I will make only a remark about that a little bit later. Okay. So as I mentioned, so we'll talk mostly about transformers as binary classifier, yeah, of strings. That is, it's a language recognizers. Yeah. Of course, transformers can do more stuff, yeah. But at least if you want to understand anything, as we know already from like computability theory, we want to be able to look at something as much simpler object first. Okay. So by the way, if you have any question at any time, just feel free to stop me. Okay. So I'm gonna. Okay, so before we go through some of the models, some of the main models of transformers, yeah, I want to first just make a general remark first. So one of the things that you'll find out about the field is that there are really many possible variants of the models that people have proposed. The reason behind it is there's really a lot of parameters that one can really look at, yeah, and all of these things give rise to different models with different, often with different expressivity. So, for example, one of the things is something about precision. How much precision do we allow, yeah, and what kind of attention mechanism do we allow? Are we allowing uniform or non-uniform models? And also, last but not least, you also want to ask how much do you allow, what kind of positional encoding do you allow? Yeah. So this is only like some of the questions, but there are actually even more parameters out there. Yeah. So I guess what I want to say is that if you see there's a lot of different models, you know, like with a table of so many things. Yeah. So please don't feel discouraged. Okay. So let's try to take a simplistic view of transformers first. So what is a transformer? Right? So a transformer as a language recognizer, so I'm going to have like some inputs like this, A, B, so a text, yeah, a string, A, B, A. So as I mentioned, so given this, what you're going to do is you want to just, in our case here, because it's a binary classifier, you just want to output 0 or 1, right? But transformers are actually, you know, models that extend deep neural networks, yeah, like feed-forward neural networks. That is, they actually don't work on text, but they work instead on vectors. Yeah. So what you need to do first is you need to first convert them to vectors. So for example, this is the simplest one, hot encoding. You can embed A as 1, 0, B as 0, 1, and so on and so forth. So now you get a sequence of vectors. And what I'm going to do is that I'm going to run this through a transformer, and I'm going to get also another sequence of vectors as an output. And at the end, I want to decide whether or not it's accepted or rejected just by, you can do it differently. But one way of doing it, for example, you can just take a linear combination of the last vector and just check if this is like less than 0. Okay. So this is just a random way of doing it. You can do it equals 0, bigger than 0. There are many different ways of doing it. Okay. Now, there's also another thing that people usually use, as I mentioned here. There's something called positional encoding. So positional encoding is so when you embed this A, B, A, yeah. Sometimes you also embed the position, some kind of positional information to the vector. For example, this is at position 1. I can put 1 here, and then I can put 2 here, 3, 4, and so on and so forth. Yeah. So this kind of positional encodings that people use, in practice actually can be quite complicated. Some people use sinus, cosine, and so on and so forth. So yeah. But so this is there are different kinds of PEs that you can use. Now, okay. So that's a transformer, but actually this box here is actually not just a single box. Yes, it consists of a number of layers. So what you do is that you run through all of these layers one by one until you get to the end, just like a normal feed-forward neural networks, deep neural networks, for example. Okay. So I'm going to concentrate on just to define a little bit, yeah, on how it works. just for those of you who've never seen it. So transformers, this is a case of transformers using one of, let's say, just only with one layer, yeah. So when you have more layer, then yeah, just simply compose them as functions. Okay. Right. So each layer is equipped with several information. So usually you have some affine transformations, just linear transformations plus a constant, yeah. And then you have this piecewise linear function. So this piecewise linear function is actually simply just a composition of linear transformations plus a ReLU. Yeah, so ReLU basically just check whether or not it's 0 or it's maximum of 0 and a number. Yeah. Okay. So this we call this piecewise linear. I mean, I don't know why, but that's what they call it. Okay. So all right. So once you have this, so you have this information. So this can be encoded finitely. So the question is, how do you compute this W1 up to Wn's, right? So and then in order to compute this, the first thing that you need to do is to compute the so-called attention matrix. Yeah. So because as you can see here, this is V1 up to Vn. So what you need to do is you need to be able to somehow so for you need to come up with W1 and up to Wn, right? So for each of the V1, the best thing to think about it is to simply look at so each position can communicate with any other position. Yeah. So this is basically why you want to come up with some kind of matrix here that kind of determine how much communication you need to have, yeah, between each other. Okay, so so this is done by this matrix, yeah, this attention matrix, and this attention matrix, each of the cell here is the so-called attention score, yeah. So for example, here at this position is going to have the attention score between V2 and Vn. So the intuition behind it is like how much attention. So let's say this is the anchor, V2. How much attention should I give to Vn? Okay, how much attention I should give to Vn here, and this is given as a dot product typically, yeah, between this V2 and Vn, like initially preprocessed with A and Bs. Okay, so the detail is not so important really, but what you get is a matrix that is of this form, right? Okay. Once you get a matrix, well, it's n by n, and now you need to collapse it into a number, like into n numbers, right? How do you do that? Well, in order to do that, the most common way that people have done so far is to use also what people do in practice is to use softmax attention. Yeah. So basically, what you do here is that so you need to compute a number. So for example, like let's look at V2 here. So you need to compute out of V2, you need to compute this W2. So in order to do this, the first thing that you do is I'm going to look at this row. Yeah, I see 8, 8, blah, blah, 1. Yeah. So out of this row, I'm going to convert it into a probability distribution. So this is the intuition behind this. Yeah. So probability distribution such that for each of the position, it's going to be simply just the weight that corresponds to this 8. Yeah. So it corresponds pretty much to 8, but this is it's now become a probability distribution. Okay. So the sum of this thing should be 1, right? Okay. And what I'm going to get now is a weighted sum, yeah, of the VJs of all of the places, yeah. But the weight here is given by the probability of each V, yeah. Okay. So that's typically what people do. So intuitively, again, you know, the intuition behind it is, so I'm V2, right? I'm gonna look at around me, yeah, and I'm gonna have these how much I need to pay attention to anybody, but I want to pay attention to everybody, right? So I'm gonna pay attention to everybody, and I'll kind of like get a glimpse of what people have. Yeah. So this is essentially what you do here, like when you do this kind of a sum. Okay. Right. So this is a little bit tricky to analyze. As you can see, there are several problems. The first one is that you have a problem with the exponential function, and this you also have a problem that nobody can really get a 0, actually. This is also the other problem here. So you don't really get a 0, so it cannot be a 0. So you have to take into account pretty much everybody. And when you do analysis, it has turned out to be quite difficult to analyze. Okay. So one solution that people have looked at is to look at an approximation of softmax attention. One of them is, so this is typically called hard attention. So what you do is that, so for those values that are not really that big, yeah, so, okay, so I'm only going to look at the values that are the biggest ones. So basically, yeah, so I'm only going to look at the attention scores or the positions that have the biggest or the maximum attention scores. For example, if you look at this row again, yeah, so I'm going to have, for example, this is the biggest one. This has the, so for VI, V2 has the biggest attention score, so I'm going to only focus my attention on this guy. And in the case of V2 here, so I have only 2 places, so I will pay attention to these 2 guys, yeah? So both of them have maximum scores, and so on and so forth, okay? So the important thing is like the guys that don't have, yeah, the guys that are not really the biggest, yeah, we just ignore them, okay? This is also what people do in practice, right? We only look at the big guys. All right. Okay. So once you have the UIs, yeah, that you have computed before, what you do then will just be to do another post-processing. Yeah. So you find the value. So I'm gonna just apply a piecewise linear function like ReLU and blah blah, and then to get this WI, right? So that's essentially what you do here. All right. Right, so that's the model, and just as a summary here, we have so basically what we've seen is we have hard attention and soft attention, yeah. And if you look at hard attention, there are actually I kind of didn't mention this, yeah, but it can be mentioned super quickly. So there are different ways of picking. So if you have 2 guys that are of equal with equal attention scores. So there are different ways of breaking ties. Yeah. So the first way to break tie is to just pick the rightmost vector with maximum score. Yeah. So or leftmost if you like. Another way of doing it is to for example just average them. Okay. So this one, all of this thing gives rise to different model with different expressive power. Yeah. As I mentioned here, softmax attention transformer, so it's more complex. So people instead usually use some kind of average hard attention transformers in order to approximate that. Okay, right. So we'll talk about we'll talk mostly about these 2 models. I will mention this every now and then. Okay, so just to go through 2 more things, yeah, and then I think we should be done with the model. Another feature that people usually use is the so-called positional masking, and what it is simple. This is used a lot when you do in practice, because like typically when you look at transformers, it's an autoregressive model. So usually you look at an input, you take an input, and then you output something, and then you run it again, and then you output something. So it's basically what you can look at any given point in any position is always, you can only look at the pass. Yeah. So this is what they call strict feature masking. That is, attention scores. You can only look at attention scores of earlier positions. Okay, so let me just tell you here how it manifests. So before here, this is n, right? So it means that you can look at everybody. You can look at when you're at a different row. Sorry, let me just show you here. Okay, at any given row, you can look at everybody, right? Before, but now. So with strict feature masking, you can only look at the rows, the positions that are smaller than you. So if you are V2, I can only look at V1. If you are V7, I can only look at V6, V5 up to V1. Yeah. So this manifests in the this kind of formula here. So where you simply have the sum here, like it's supposed to n here, you get like I minus 1 here. Yeah. And also for the hard attention, you only look at the VJs, yeah, that that come before VI. Okay. So for example, the effect here would be like, before it was here 7, but now here, like, it's actually only here. Okay. So as I mentioned, the most recent models employ feature positional masking. Okay, I think that's pretty much the model. So can I ask if everybody is kind of on board? Yeah, good. Okay, so what I'm gonna do is the following. I'm gonna go through the two models, like U hat and A hat, one by one, and I will tell you what kind of results that people have come up with, and in relation to expressivity and also to verification. Mostly focusing on this, yeah. All right, so the first one, this is a very useful connection, yeah, but I will not talk about it too much. It's the connection to complexity theory. So I'm only a user of complexity theory, and this is like a really good application of it, for example. This was proven, like a few years ago, that U hat, the class of languages that are recognized by this U hat, are in the circuit complexity class called AC0. I don't know how many of you have heard of it, AC0? Okay, yeah, so the intuition behind it is, okay, so firstly, let me just say what it is. So these are basically problems that can be solved by families of circuits with constant depth, yeah, so the depth cannot increase, yeah, it's only like constant, and the size of the Boolean circuits only grow polynomially in the size of the inputs. Okay, and then there's some minor details that I didn't mention, that you need also unbounded fan-ins. Yeah, so for example, if you have an AND, this has to be, you need to be able to have ANDs with multiple inputs. So these are actually languages that are like can be very efficiently parallelized. But the catch behind it is that it's also pretty weak. So for example, you also know that you cannot do parity. Parity is not in U hat, yeah. So this is a deep result. I mean, of course, like complexity theory is full of results that, that are okay, so full of conditional results. We don't have anything unconditional, but this is unconditional, okay? There's no like NP complete or anything, okay? So this is like, this is known to be the case. This was proven many years ago. Yeah, quite complex proof. Okay, so let me just say super quickly here. So this gives you, how does it relate to the question that we asked earlier, right? So this like this anomaly, like the that transformers cannot do parity. So this could give you a candidate for a model of transformer that, like faithful to real world transformers, and at the same time maybe more analyzable. So this is kind of the background behind it. So okay. So that's at least, that gives you some kind of an upper bound, yeah. So what kind of things you can what kind of things you can recognize, but what can you actually do? So that tells you what you cannot do, but what can you do? So we have some results here, yeah, from these two papers. So let me just give you a summary first, and then I will go through it in more detail, yeah. So remember, one of the motivations for coming up with, for studying this, is we want to be able to have a better clean declarative language that allows you to express transformers, like if you want to write it down by hand, let's say, right? So that's what we want to do. So this is, this should be interpreted in this spirit, yeah? So we want to have a characterization of this transformers, or class of transformers, using some kind of a logic. And this logic turns out to be a logical fragment of AC0, okay? And when I say characterization, of course, the best thing would be like to have some kind of equality, if possible, yeah? And it turns out some kind of equality can be shown, yeah? And it's highly connected to the so-called star-free regular languages, or if you know LTL or first-order logic, so it's all the same thing. Yeah, and this actually also tells you when you look at the proof, it actually is it's an effective translation. So we know that if you only just want to, if you're just interested in U-hat on its own, yeah, that has fixed precision and only strict feature masking, we know that this is verifying this. So I mean, like emptiness and so on and so forth is decidable. Okay. So what is this language? Well, I mentioned star-free regular expressions. Yeah, so I'm sure some of you, or maybe most of you, have heard of it. But in terms of verification, and also to be closer to the model, we can look at this LTLF, pure pass LTL, finite LTL, finite trace LTL instead, which Moshe Vardi has looked at a lot in the past 10 years or so. Okay. So the model is very simple. You just basically it's just normal LTL, yeah. But what you do is that you have instead of looking to the front, you actually only look backwards, yeah. So I can have I can instead of next, I have like the inverse of next, which some people call yesterday, yeah. And instead of until, I have like since, yeah, right. So the meaning of this thing is really what you expect, yeah. Yes, maybe some kind of quirkiness just for the purpose of translation. Sometimes we make it strict, yeah, but this is just for technicality, yeah. Okay, so this is just basically the previous guy, and phi as psi is basically just walk backwards. Walk backwards, and everybody has to be phi, and at the end you have a psi, right? But so we use the strict semantics here just because it's easier for the proof, yeah. Now, if you have LTL, of course, you interpret it at the beginning, yeah. But if you have LTLF pure pass, yeah, then you interpret it at the end of the string instead of the beginning. So you really just have the same thing, yeah. Okay. So I will give you like a bit of a flavor of how the translation goes, yeah. Like nothing really deep, yeah, but I'll just to give you a flavor. But one thing that can be just before that, I just want to mention super quickly, if you look at the translation on its the translation itself, yeah, and want to be able to do verification, then of course complexity matters, yeah. And it turns out you can do pure pass LTL-F, yeah, to U-hat in polynomial time, yeah. So this is so it's U-hat is at least as succinct as LTL, yeah. But it turns out it's actually also exponentially more succinct, yeah. So in the sense that you can be also, if you want to verify U-hat, it turns out it's actually 1 exponential higher, which also incidentally could be a potential domain for automatic verification. Nobody has really looked at it, yeah. But just to mention that, I think it could be maybe an application of IC3 or something like that. Okay, so I don't think there's a lot of time, but I will just maybe, in the interest of giving you a bit of a flavor, I will just go through this super quickly. So let's take a look at this very simple formula, yeah. Okay, this very simple LTL formula. This corresponds to this regular language. Okay, and let's say the input is A, B, B, A, A. Okay, so as I mentioned, so the strings have to be first converted to sequence. So I'm gonna use the encoding that I had before, the one-hot encoding, yeah. So this A, B, B, A, A is gonna become this this sequence of vectors. I'm not gonna use any positional encoding here. So this is basically just gonna be the input like that. Okay, so the key idea behind the construction of U-hat is you first want to label each position I, indicating whether or not the formula psi is true at for any psi, for any subformula psi of the input formula here. So I'm gonna label it with information that indicates whether or not psi is true at that position. Okay, so this is just like a standard. If you know the standard LTL to automata construction, it's a little bit like that, right? Okay. So after first layer, so if I just like label it, I'm gonna, so I will tell you how to label it, but I'm just gonna tell you how the proof goes. So first I'm gonna like label 0, 0, 1, 1, 1. So basically this because, for example, here 1, this is I'm gonna look at the I'm gonna look at this ASB, yeah, as the first subformula, and the second one is the entire thing. Okay, and then if you look at the first one here, this is true, 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 like this one here. Okay. And then after for the second layer, I will do the same thing, but I will just keep extending. So the output of the second layer is just going to be the same thing, but I'm just going to extend it by one more information that indicates whether or not the entire formula is true at that position. So if you have this information, what can you do to read out whether or not W is true? You simply have to look at the very last position, and just the very last position of the very last vector. Okay. Okay. So maybe just let's go through just one example, idea for layer 1. Layer 2 is pretty easy. Okay. So the idea here is, so this actually has several sublayers. But if you have something like phi as psi, what you want to do here is you want to find the first position. Yeah, you want to find the first position such that not phi or psi is true. Yeah. So this is because the semantics, you need to find somebody such that psi is true. Yeah. And then before that, phi has to be true, right? So I'm gonna label each position with not phi or psi. Okay. And this actually requires two sublayers, just some details. Yeah. This actually turns out to be just B, yeah, so we don't actually need to do anything because we already have the information of B. Okay. And once you find this position, yeah, what you want to know is whether or not psi is true, right? Because at this position, psi has to be true when not phi is when not phi is false. So you need to know that psi is true at that point, right? Okay. And in order to do this, yeah. So first you find that position, and then what you need to do is just need to the information here, yeah. So whether or not, so if you can find it, yeah, then this formula is true. That is, this formula is true. Sorry, if only if it's found, yeah. This such a position is found. If only if what you forward here, yeah, the value here is 1. Okay. So you want to know that psi is true, right? Okay. So what you do here is that just to fill in a bit of details. So what you do here is just the attention score here at position J here should have this value, as I mentioned. Yeah. And here so you find the rightmost position Vj. So if it does not exist, actually it's okay, yeah, because it'll just be 0, and you'll just find this degenerate case. You'll just find the next guy, and the value is 0, so it's okay again. Then once you found this value, if you have this value, then you simply just have to map the n here. Like you need to map this vector here into just vi here extended with the value of this. Okay. And again, this is a bit of hand waving, I understand, but what's going on here is that this value here, you can simply, if you have a vector, you can simply just use an affine transform to just project it to one of the values. Okay. All right. So that's just an example of how things work, and the same can be done as well when you have an x. Yeah. So I'm gonna skip that. Yeah. Okay. Right. Okay. So any question? Sorry, I didn't. Yeah. Yeah, so in this particular case, actually, I don't need anything more than just bits in this particular case, yeah, because this is a very basic LTL. So again, the full general result, actually, you can do more than LTL, yeah, but I just want to connect it to LTL because it's you can actually verify it. Yeah.
That makes sense. And are we going to sort of use sort of larger size arithmetic later, or?
Yeah. So this is we're gonna talk about that in when we deal with AHAT. Yeah. Okay. You have more questions?
Okay, thank you.
Yeah. Okay. So yeah. So so it turns out that you actually have a full characterization if you sufficiently restrict the transformers, especially if you talk only about positional encoding with fixed precision. Yeah, so fixed precision, I think you can think of it like, let's say you have, I don't know, floating points, let's say, yeah. And you still have masking as well, like before, yeah. So this can also be converted into LTL, yeah. Okay, so this, it actually is an equality in this case. So this is, let's not go through the detail, but I think just the key ideas here is that it turns out if you look at UHAT, if you think about it, you cannot actually generate really new vectors. You know, like all the values that you have already computed already exists in the input somewhere, right? Because you only pick a winner, and then you just have to do an affine transform. So it's basically you can symbolically write it down in terms of the input values. So you cannot really generate like infinite number of values here. Okay, so this is important because like if you have that kind of result, this also explains that you can actually also compute an automaton, in fact a transducer, yeah, and each layer can be converted into ladder-to-ladder transducer over using a fixed alphabet, yeah, and their compositions also a transducer, and if you analyze it more closely, it turns out to be a counter-free minimal DFA, which is basically just LTL, yeah, okay, right, okay. So that's essentially like how it's not really, there's nothing really deep here. Yeah. Yeah, but what actually turns out to be, as I mentioned, if you look at this analysis here, it turns out that you do need to, in the worst case, generate an LTL that is exponentially large. Okay, so I think that's all I want to. Okay, no, just to recap this again. So I think an open question is, can you verify you had efficiently in practice, let's say with property-directed reachability? Okay, so time, right. So I want to just connect it back to what people have looked at in practice. So UHAT seems to be like a pretty nice kind of model, yeah. So it's a good approximation, in fact, for transformers under bounded precision regime. That is, for example, using floats. There's some consistency with experiments. For example, parity not expressible, so it's also predicted by the theory. But the problem here is that if you look at stuff like, so there are some problems. So the first one is that there's this language called majority, yeah. Majority simply like, you have A's and B's, yeah, a string of A's and B's, and this in the language if the number of A's is bigger than the number of B's. So this is not a regular language, yeah, okay? So this seems learnable, yeah? And there's another one. This is kind of the opposite side. There's something called flip-flop language. There's sigma star B E star, yeah? This is expressible by UHAT, but actually it seems to be non-trainable. At least people have difficulty training it. So there's a way to reconcile this, yeah. So there's a way to resolve the inconsistencies. Number one, which is not very nice, I would say. So transformers can actually express majority only for small inputs. So small inputs could be actually whatever it is you care about, yeah. We don't know. The theory actually is like asymptotic, right? So, but it could be anything that you care about. So for something large, so it does not recognize majority anymore. So it could be, this is one possible explanation. I think this is true, but then it kind of renders the theory not so super useless, not so super useful, yeah. So what, in order to reconcile, like in order to resolve the second problem, what people have is they actually came up with a subset of UHAT, yeah, and they have shown that the characterization actually is LTL pass. Yeah. So it's basically, it just means that you only have the pass, yeah, but you don't have S, you don't have X, yeah. So you only have like the pass. It's a bit like it's equivalent to future, but you move backwards, right? Okay. So in this case, if you look at this, then the flip-flop language is not in LTL pass. So this is maybe a better model from that perspective. Okay, so I think that's all I want to talk about for UHAT. I will just talk about AHAT here. I know that I don't have that much time, but I will just, in the interest of showing you something a little bit more, I think it's actually more interesting maybe, I will just at least show a couple of slides. Okay, so let me just begin again with the connection to circuit complexity, not really long, yeah. So before it was in AC0, but now we know that this is an ATC0. Basically, these are the class of languages recognized by, AC0 circuits, but you also have the majority gates as well. Okay, it's known that you can do like arithmetic, multiplications and stuff like that here. So it's still also efficiently parallelizable. Yeah. In fact, if you have circuits up to log depth, they're still efficiently parallelizable. So it's quite consistent with what people see in practice as well. But the problem now is that this doesn't actually help us anymore to show any unconditional inexpressibility. So yeah. But what we can say here is, what about what can we express? Yeah. And this is, I think, a more interesting question. And here we want to approach the problem from a similar kind of perspective. That is, we take some kind of a logical language, and then we want to see what can you express using this. Now, before moving forward, I just want to maybe make a remark quickly. So we know that in AHAT, we can actually do some kind of majority in all these things. Yeah. So that's quite nice. So, and a logic that can sort of allow you to do this is actually this so-called counting LTL. Yeah. So I mean, I make it like they have a name for it. It's called CRASP. Yeah. But this is simply like counting LTL. So we have like LTL-F pass. Yeah, which is what I wrote before. Yeah. That was a subset of UHAT. Yeah. But now you add counting on top of it. So let's take a look at it. What can you really do here? Okay, so if you look at the logic, the special part is actually only this one, yeah, this sharp phi. So otherwise, it's pretty much it's pretty straightforward, yeah, just like LTL. So what is this here? Sharp phi. So this actually only counts the number of, so at position I, you only count the number of positions that are to your left, yeah, that satisfy phi. Okay, so this basically just you only do some kind of counting, yeah, where the number of times phi holds. Okay. What you can show here is that this is quite interesting because it's actually strictly subsumes LTL-F pass, yeah, that we've already seen before. So it strictly subsumes that. So the reason behind it is that you can actually express this pass, yeah, that is F minus 1. F inverse phi, you can simply just write it down like this, no? Sharp phi bigger than 0, no? So phi has to hold at least once next to the left of me, right? So you can write it down. But of course you can do more, not just regular languages. You can also do like one-dict language, for example. You can do majority, you can do one-dict language. So here, this looks a bit like, maybe you think it's like a typo, but it's not. So what it says here is that at any given position, the number of open brackets have to be at least as big as the number of closed brackets. Yeah. So that's basically what it is, right? So this is that's okay, and this can be expressed in CRASP. You mind if I have 5 more minutes? Is that okay?
Okay.
Yeah, because like yes.
Because we will have 5 minutes for the break.
So you have 6 minutes for. I see. So I thought it's 1 hour, right?
1 hour. Yeah. I mean, okay. I saw that you want to have 1 hour and 5 minutes.
No. I didn't. No. Okay. Okay. Let me just show you here. So we have similar kind of result to UHAT here. Yeah. one can show that counting LTL F pass can be expressed in A hat as opposed to U hat here. But there's some extra things here, like so we have to use positional encodings here and also with strict feature masking. So this is a similar kind of result. So you have to somehow deal with the this. You have to use A hat here instead. If, for example, if you're interested in softmax, yeah, so you cannot really just do. At least it's not known how to do it in softmax, yeah. So you can use uniform layers, but you need something. You either need some kind of like maximum somewhere, or you need some kind of layer norm. So that's so there's an open question here. If you wanna, is it possible to express CRASP in softmax? It's an open question. I don't think I want to. All right, maybe just super quickly. I just say it quickly here. In A hat, what you can do is that you can count the number of times, right? So you can look at so if you so you're interested in like sharp phi, right? So you want to get the value of sharp phi, but what you can do in A hat is actually not sharp phi, but what you can do is a sharp phi divided by 1 or minus 1. Yeah, but you look at frequencies opposed to doing counting. Yeah, so you can do that here in A hat. Yeah, because what you do in A hat is simply you look at the number of times something is true, but then there's divided by the divided by, because you do average, right, instead of counting. You know? So this is actually a problem, because when you actually want to express CRASP, you don't want these things because every position has a different value. So this is the crux of the entire problem with all of the translation, and I can tell you that, yeah. And everybody solves it using something different, yeah. And it's not known how to do it, cleanly, yeah. So what we do here is that in our case, we get rid of this these things using positional encodings. In particular, we use the help of this I and I square in the positional encoding. In order to help you, you need to pick some kind of value j that actually annihilates, so to speak, yeah, this thing. Yeah, so that's the way we do it, but other people do it differently. Okay. Now, okay, so this is just a bit of detail, like technique-wise, right? But why do you care about CRASP anyway, right? So this is what we should ask. Why do we care about this? Now, I think the answer to that is provided by this paper, and I really like this paper a lot, yeah, because it shows you this has a lot of experiments that takes CRASP languages and shows that whatever you pick so far, at least, yeah, it seems to be learnable by real-world transformers, yeah. So using pretty controlled setting, so this is pretty nice set of experiments. So the authors also conjectured that CRASP captures languages that are efficiently learnable by real-world transformers. So this is a formal version of the so-called RASP conjecture. Actually, this is not true. Yeah, so we disproved this recently, but I think this is still a very nice language. Yeah. So what I mean by we disproved it recently, in the sense that there are actually more things that can be learned. Yeah. So as opposed to there are less things. I think I maybe just want to mention super quickly. So CRASP, the problem is that you have linear counting, but you can also do polynomial, right? So for example, like, you know, you can do something similar like majority, but you have like here to the power of k. Yeah. So it turns out you can actually do also polynomial counting. And we proved this here, that experimentally and also in theory, that not only can you do polynomial counting, we also proved that you can actually also do you can also show that they can actually recognize such languages. Yeah. But the important thing here is that this is the if you assume it's permutation invariant languages, then you can do, like, you know, polynomials. Like semi-algebraic just simply means any system of polynomials. Yeah. Okay. So this is actually, we showed that this is also bigger than CRASP. Yeah. So an open question is, of course, that is asked by quite a number of people. Can you actually combine CRASP and polynomial counting to get another logic? And is it actually also in, let's say, A hat or softmax transformers? And nobody knows. Now, that's actually a problem, because if you can show that, then you also get this problem, this corollary by default, yeah, that a hat, even like without any positional encoding, is actually also undecidable, because you can just simply reduce from solvability of the Diophantine equations. So that is a problem. But you can ask then, okay, so maybe I don't want these polynomials, and I just look at CRASP. What if I just only look at CRASP instead? Yeah, so I can only do semilinear counting. So maybe I can now be decidable again. Now that's actually a problem, because we also show that this is also undecidable. So because we can also embed the Diophantine equations to CRASP in a satisfiability preserving manner. Okay. All right. Okay. So, I mean, okay, from a theoretical standpoint, maybe not so cool, yeah. But I think it's actually cool, because I'm a verification person, and I'm not afraid of undecidability, yeah. So, and I think the next question is, okay, so can we actually employ some verification techniques for CRASP? And I think this is a really cool problem, because I mean, we only started looking at it, yeah. But the question is very much related to some problems that you look at when you look at this language like Lustre, yeah, which is related to synchronous data flow programs, and which can be reduced to like something like Z3 or CVC5 and so on, right? So we are exploring this this direction, and it seems to be like there's some interesting result that you can get as well here. Okay, so I'm gonna skip the entire chain of thought stuff, yeah. All right, and I'm just gonna mention the future research directions. So we've mentioned like different models here, yeah. So I think there's still a lot of questions about expressibility, like coming up with a better logic, and I think I've mentioned repeatedly the challenges in verification as well. It's not clear. And another thing that I didn't mention here is like trainability. I kind of indicated that, yeah. But it turns out there's something really nice here that has been shown recently, that some kind of notion of trainability is actually equivalent to decidability of language equivalence. Now, people in different companies and also in different research institutes have looked at other architectures, yeah, like hybrid models of linear RNNs and transformers. So this is like a really big thing that a lot of people are looking at. And finally, I also should mention that we've only looked at text, yeah, but there are also other kinds of transformers, like vision transformers, like speech recognition transformers and time series transformers, that I think are people have not looked at at all. So with that, I thank you for listening, and I guess we have two minutes, but I'm happy to answer anything that you have.
Does it work? Yeah. Okay. Thank you for the interesting talk. It's a bunch of interesting work. I have a question regarding. I think sort of this focuses on hard attention. You sort of said that soft attention is quite tricky, and I think you gave some indication as to like what might be different in that context with soft attention, with like a different sort of real world architectures. But I wonder what would happen if you like take, I don't know, a trained model that is using soft attention, sort of interpret it with hard attention, and then sort of by that you can sort of say, can you for instance translate or compile that model into LCL, and sort of what you get sort of this very discrete, very concrete.
There are some experiments on that, and I must admit I have not really looked at the experimental results, but I know some people who are experimenting on that, and they have claimed that there are some good results, but I haven't really seen them published, so I cannot really give you so much comments on that, unfortunately.
Okay, so maybe in the future we might see some papers.
Yes, yes.
Cool.
Yeah.
Thank you.
Thanks.
Thanks for the great talk. So my question is about the data. So I understand that it's a really good idea to capture the class of languages that transformers capture, but when I also consider the training data in the question, then I would imagine that the class would be perhaps significantly smaller? Or for example, can I look at questions about, okay, if this is the kind of training data, then the expressivity is much smaller. Has this been explored?
So if you want to look at, I guess it kind of depends on what you mean by the training data here. So people have looked at trainability, maybe, if that makes sense, but maybe you're looking at something different, not exactly the same.
The motivation for my question is, well, in real life, if I'm using an LLM, then it's a fixed LLM with fixed weights. And I should.
But what you care about is not as in learning, you care about something that generalized, no? I mean, if everything is already in the training data, then it doesn't make sense. So people usually have the notion of at least length generalizability, So you want to train it up to, for example, length 100, and then you want to be able to predict consistently up to length 200, let's say. So people have looked at something like that, and this is connected to this trainability that I mentioned, So there are notions like that, but I also will say that it's also a little bit, the notion is a little bit not very clean so far. So this all, I mean, all the works on this in the last, less than 2 years. So,
Thank you.
Thank you.